So today we're working on Unit 5, solving equations as we have been, but we're going to focus on inequalities today. So inequalities are statements that compare two expressions with a less than, greater than, less than or equal to, greater than or equal to, or even a not equal to symbol. Their solutions are regions or sets of numbers. So what that means is that there's obviously more than one answer. So we're going to be graphing our answers on a number line as well as stating them in any of our other types of ways to show answers. So when we're solving just linear inequality, starting off with the basics here with just a line, it says to treat the problem like an equality. So remember to switch the direction of the sign if you divide by a negative, and that's really the only funky rule in there. And then we do want to test our solutions back in the original problem to make sure that they work. So in tackling a problem like negative 2x plus 7 is less than 15, we're doing kind of that reverse order of operations thing where we have to kind of unpeel the layers off of our function here. So I have negative 2x is less than 8 after I subtract 7 from both sides. And here I'm going to divide by a negative 2. I'm not really sure what happened here. I'm dividing both sides by a negative 2, so I'm getting x, and 8 divided by negative 2 is negative 4, but I divided by a negative, so I just want to switch my sign there. So x is greater than or equal to negative 4. So that's one way that I want to have you write your answers. And then the other way is that I do want you to draw a number line for each of these, and you don't need to be super specific. Sorry for fumbling my words there, but I only care about negative 4, and then I know that x needs to be greater than it. So if you recall, greater than is going to go to the right here. And it's an open circle with these guys, and then these guys up here, the equal to is our filled in circle. So less than or equal to is open, greater than or less than or equal to are going to be filled in. And that would be our solution right there, like that. If we were wondering how to test this, I'm not going to pick negative 4 to try because negative 4 should give us something that equals 15. You can try just one number in the set. So that's going to be any number on this side. So let's try the number like negative 2 because we know that that's going to fall somewhere in this set. So that'd be negative 2 times negative 2 plus 7 is less than 15. 4 plus 7 is less than 15. And 11 is certainly less than 15, so we know we kind of have that set right. You don't have to check it like that every time, because obviously if we picked a different number, they should all work, but it's not really helping you find this exact value of the boundary. But it is a nice way to just make sure that you drew your arrows in the right way, and that we did switch that sign when we did the negative. So that's really it for solving linear inequalities. I want you to try examples 1 through 4 in your packet now. All right, so the next section here is to solve an absolute value inequality. But first we need to take a look at the two main types of compound inequalities, which means we're basically going to have two different answers or two different numbers. So we need to look at the two cases of the and then the or. So the first type is our or inequality. And to do these, you're just going to kind of solve them both separately. So here I have one function that is x plus 3 is less than or equal to 2. So I would just subtract 3 from both sides there, and I get x is less than or equal to negative 1. And then I have the other one here where I'm just going to divide both sides by 3, and I also have x is greater than 3. So when we put this on the number line, why this is an or becomes a little bit more clear. Again, the numbers that I'm concerned with is a negative 1 and then this positive 3. And we're saying that x is less than or equal to, so that's our filled in circle, which I want to do like this. And it's going to be less than that. Or the number can be bigger than 3, and either of those situations work out. So it's an or statement because no number is both less than negative 1 and greater than 3, but there are plenty of numbers that either fall into the case of being less than negative 1 or they fall into being greater than 3. So that's what the ors look like. There's kind of space in between and you have your arrows going off in either direction. If it's an and compound inequality, you want to kind of solve it as 1. So I'm going to rewrite this real quick. 13 is greater than or equal to negative 2x plus 1. And that's going to be, which is greater than 9. So as we're doing to 1, we do to all 3. So the first thing I'm going to do is subtract this 1 from all 4 places. So I have, or all 3 places. 12 is greater than or equal to negative 2x, which is going to be greater than 8. And now if I'm dividing by negative 2, I'm dividing everything by negative 2, which means our signs are going to change. And we are going to get a negative 6 is now less than or equal to x, which is going to be less than negative 4. So if I were to put this onto my number line here, again, the numbers that I'm concerned with are negative 6 and negative 4. And you just always want to make sure that our number line is correct, going from smallest to biggest. My negative 6 is getting that filled in circle because that's an or equal to, and my negative 4 is not an or equal to. And then this one, so x is going to be bigger than negative 6 and less than 4. So if we're filling in this line, what this is really saying is that any number in between these two is both of those things. It is bigger than negative 6 and it's less than negative 4. So that's really where we're coming from with that, is that when it's filled in and those arrows are kind of pointed at each other and it's a contained set, that's going to be an and versus the or. And as we move on here, I did give you guys a chart. So when we're dealing with absolute values, they're always going to be compound inequalities. And if it's just the absolute value of x, what we're saying is that the distance is equal to negative a or is equal to positive a. But when we come to an inequality like we are here and here, if we are given a less than symbol, we kind of have the and situation happening, and the greater than symbol is going to kind of be an or. And so let's see how that kind of plays out here. So to solve the absolute value inequality, like 2 plus 3 times the absolute value of x plus 4 is greater than or equal to 14, we're isolating the absolute value expression, rewriting it as a compound inequality, and solving each part for x. And then we will graph it on the number line. And then I just want to pay kind of close attention right here to where it says when you write the second opposite equation, you know how we usually set one equal to a and the other one equal to negative a, we're going to change the sign on that negative a one. So let's get started so you can see what I mean. So the first thing I'm doing is, like we said, I'm peeling those layers. So I'm going to subtract 2 from both sides. And I get 3 times x plus 4. If my and is greater than or equal to 12. And then I'm dividing both sides by 3. And here's my jumping off point. I get x plus 4 is greater than or equal to 4. So now from here, this is where I write my two equations. My first one is going to be x plus 4 is greater than or equal to 4, kind of just like what's shown there. The other one is we're never changing what's on the inside of our absolute value. It's still an x plus 4. But now I'm switching my sign, just the direction, and I'm negating my a value, which in this case is 4. So you want to solve for both of these. So in our first situation, we're going to get x is greater than or equal to 0. And in our second situation, we're getting x is less than or equal to negative 8. So if we were to put this on our number line, we have our concerned numbers, which are negative 8 and 0, and both of those are equal to, so I'm going to fill them both in with some solid dots, and now I just have to figure out what directions they're going. So x is greater than or equal to 0, so that's going to be bigger, and less than or equal to negative 8. So this is our or situation, kind of like we said that too, because it's a greater than symbol, and our greater than symbol is generally going to be our or. So if you follow those rules, and then just make sure to check your solutions, and on try problems 5 through 8 in your notes. And now we're going to get into solving quadratic inequalities. So we know that we're going to get into some factoring and things when we have a quadratic here. But so take x squared minus 4x plus 1 is greater than 6, for example, and we're going to write the related equation, and we're going to find our 0, so it's going to mean setting it equal to 0 and then most likely factoring. And then these become our critical values. So then we graph these values on the number line, and then we actually have to test an x value in each interval to see which holds true, and then we'll shade from there. So what this means, it is possible to get we need to decide if it's an or an and, as in are we drawing our arrows into each other or are we drawing them away from each other, and I'll kind of go that as we go here. But no matter what, our first step is always set our function equal to 0. So in this case, I'm actually subtracting negative 6 from both sides. And so my equation is x squared minus 4x minus 5 is greater than 0. So then I want to be able to factor this guy, and it factors to x minus 5, x plus 1 is greater than 0. And now if we set each of our factors, so x minus 5 equal to 0, we'd get that x is equal to 5. And if we had set x plus 1 equal to 0, we would have gotten that x is equal to negative 1. So this is where this really comes into play here, is that we're going to take our number line. This is how it's different than like a linear and absolute value, is we take our number line and we put our critical values on it. So we have negative 1 and 5. And what it means is to test the appropriate regions is that we need to see if this right here is the set of solutions, this right here, or this over here. So you're going to take a number that is to the left of our region. So perhaps we would take one that's within our region. So I'm going to use 0. And then one that's bigger than our region. So I would try x equals 6. When we plug negative 2 into our original kind of equation over here, we get that 13 is greater than 6. So what I'm doing is negative 2 squared minus 4 times negative 2 plus 1, and I get 13 is greater than 6. If I plug in 0 for that same thing, so 0 squared minus 4 times 0 plus 1, I get that 1 is greater than 6. And if I repeat that same process with 6, I get that 13 is greater than 6. So this one holds true, as does our last situation, but this one does not. So 0 is not in our interval. So right here is not a proper situation. So if I were to just redraw my solution set, I had negative 1 and I had 5, and these were going to be open circles. Anything less than negative 1 is an answer, and anything greater than 5 is an answer. So the way that this one would look, you would say that x is less than negative 1 and greater than 5. Just like that. So that's what it means. So you want to make sure that you always are testing those intervals. Use some good test points that are in each of those 3 sections, and then use that to help guide you through as you put your answers and solutions on the number line. And you can try that for problems 9 through 12. So go ahead and get started. Okay, so after quadratics, I do want to tackle the concept of radical inequalities. So to solve a radical inequality like 3 times, I'm doing the cube root of x minus 4 here is all greater than 9. We're going to follow the same steps as solving a radical equation, but we are going to check for extraneous solutions when we're done. So this is a little bit more of a straightforward approach. So when we were solving a radical equation, we always wanted to isolate our radical. So if I'm looking here, this whole chunk that I just squared is my radical, and I got to get rid of this 3, so naturally I'm going to divide it from each side. So I have the cube root of x minus 4 is greater than 3. So now to undo this kind of box section again, I would want to cube it. So I'm going to cube this whole side, and those inverse operations are going to give me just x minus 4 on the left-hand side, and whatever I do to the left-hand side, I have to do to the right, so I end up with a 27, or 3 cubed, on the right. And then I'm going to isolate my variable, and I just get that x is greater than 31. So then they only say you got to check for those extraneous solutions because we know some funky stuff happens when we're taking cube roots, square roots, and the like. So we would just plug it back into check. I would do, and you can do this mentally, but the cube root of 31 minus 4 is greater than 9. This is 3 times the cube root of 27 is greater than 9. So this is 3 times 3. And now we know why it's equal to 9. So obviously 3 would make it equal to, and that's good. But we would definitely need this number to be bigger if we want this side to be bigger. So this checks out. And then just as always, so we get in a good habit of it, we're just going to throw that on a number line. It's an open circle, and x is bigger. So we're going to move our arrow that way. So if you're comfortable with this concept, we would think we're ready, but this was a cube root, so that's like a really good place to start. And if you have an odd root like that, you're going to do it like this every single time. So that's going to be like problems. Well, I didn't give you any examples like that because it's a little too easy. But if we look at our next example with an even index, and this is what problems 13 through 16 on your note sheet here is going to do for you, we also need to add a layer because we have to think, wait a minute, we can't have negatives underneath our radicals unless we're getting into the world of imaginary numbers. So we are also going to want to find the values where the radicand is non-negative, and I'll show you what I mean. So kind of even before we start the problem, I'm going to take my radicand, which again is this section of numbers right in here. So we want to make sure that that number in there is a positive number. So kind of off to the side, I'm going to do it in the upper right-hand corner here. I'm going to take my radicand, 2x plus 3, and that number has to be greater than or equal to 0, whatever x is. So now I'm going to subtract 3 from both sides. 2x is greater than or equal to negative 3, and divide by 2. So I know in the end that whatever my answer is, my field of x's, it also has to be greater than or equal to negative 3 halves, because it does me no good if I get x is equal to negative 5, and then that gives me a negative 7 underneath my radical. That will do me no good. So once we kind of did this is what I call like the side work. We're going to leave it and we're going to forget about it for now. We're going to come back here to hopefully a nice clean problem. And we're just going to start by isolating the whole radical. So in this case, we're only adding 4 to both sides. So I have the square root of 2x plus 3 is less than or equal to 9. So to undo this square root, the only thing we know to do is to square it, and we're going to square both sides. That gives me 2x plus 3 is less than or equal to 81. Okay. So now I'm going to subtract 3 from both sides. Subtract 3. And I get 2x is greater than or equal to 78. And then divide by 2. X is less than or equal to 39. Okay, so that is what we are working with. But now what I want to do is use my number line to guide me, because I know that it has to be less than or equal to 39, which is here, and is going to be going this way. But we also said, now coming back over here, that it has to be greater than negative 3 halves, or equal to. So that would be coming here. So our solution is really that x can be any number sandwiched between the two. And if we only got this answer, or we only got this answer, we'd be opening up our solution set to way more answers than actually belong. So while there is quite a large solution set here, it is limited to the numbers that are bigger than or equal to negative 1/2 and less than or equal to 39. So really use this to help you, as you're going to find that sometimes this is kind of that non-negative radicand is kind of neutralized, that it was already part of the answer, and so you'll have one-sided solutions. You'll see something like that in number 13, but go ahead and try 13 through 16 in your note sheet now. Okay, this is our last concept, I promise, but since we're talking about all types of inequality signs today, I want to take a look at solving exponential and logarithmic inequalities. So they can be solved in many ways, just like their equal counterparts. We know we have our inverse relationships, we have different properties. Sometimes we're logging both sides, sometimes we're using, we only have to do the one, or we're turning a log into an exponent. So we're going to pretend that there's an equal sign there. But then we want to make sure that we are using the right relation, so we are going to use a test point inside and outside of our boundary, just in the end, to make sure that we're putting the right sign in there. Because I know a lot of times there can be some confusion when we're moving things from side to side here. So if I was going to tackle this first problem, this log of x squared is greater than 6, we know that one of the things we could do is we could turn this log into an exponential. And what that would look like, and I usually draw myself my little e, and you can also think of this as raising both sides to the 10th power. What we get is 10 to the 6 is greater than x squared. And so if I'm trying to square root, if I have x squared and I want to know x, I can just square root both sides. And what 10 to the 6, square root of that would be 10 to the 3rd, which is 1,000, is greater than x. But since I am switching this around, I just want to make sure that I can do this the right way. So I would try a test point. I would try 1,000. I would try 1,001 for a number that's bigger. And I would say, oh, I'm going to try the number 2, just any number that's smaller. Okay. So again, what I'm trying to do, and I'm doing this right in my calculator, I'm going to do log of x squared, where I'm plugging each of these 3 numbers, I don't want those to look like negative signs, each of these 3 numbers in for x, and see if I get a number that is greater than 6. And so when I plug in 1,000, I get 6 right on the dot, and that's that's not going to be part of our solution, but it'll work. When I do 1,001, I get a solution that works, but when I put in 2, I do not get a number that's bigger than 6. I get a number that is much smaller than 6. And again, you're just plugging this right into your calculator. No hard math to deal here. So what this is saying is that I need a number that's bigger than 1,000. So when I was originally looking here, I thought that x had to be less than 1,000 because I kept the sign the same. So I kind of want to hold out on my signs until the very end so that I can say x has to be bigger than 1,000. And that has to do with me kind of switching the positions of my numbers around when I did my little e trick here. So kind of ignore the sign until the very end when we can determine using test points, which is mathematically something that we've been doing constantly. It's repeated. It's not a special rule. That's going to help us make sure that we get the right answer in the end. And if I were to throw this on a number line, we know we would have 1,000. It would be an open circle, and we want numbers that are bigger than it. Moving on. Here are my exponentials. We want the same bases. We want the same bases whenever we can. If we can't, we know we would take the log of both sides. And if those were base e's, we would take the natural log of both sides. But I can rewrite 4 here as 2 squared, which would give me 2x minus 2 when I distributed. Okay? And so now that we've both base 2, we can write the equation x is less than or equal to 2x minus 2. And if I were to solve this, I would bring my 2 to the other side and subtract an x, and I'm getting that x is greater than or equal to 2. But before I determine that, I want to try my test points. I don't believe my sign is correct until I try my test points. So the test points I want to use is definitely x is equal to 2. We want one where x is less than 2, so maybe 1, and one where x is greater than 2, which is maybe 3. So just so you guys can kind of see what I'm looking at here, here is my 2. I'm using a test point from here, here, and here as far as intervals go. When I plug 2 in my calculator on both sides for x, it works. We know it's going to work, so we're filling that circle in. We knew it was going to be an or equal to sign. Then I try my 1. My 1 does not work, and when I try 3, 3 does work. So I want to go my solutions towards my bigger numbers, and then I can go ahead and erase whatever sign that was there because clearly that's not part of my solution set. So for these questions, you're going to try 17 through 20, and you're going to give them your best shot. The answers are included, so you should definitely go through and check all your answers for all of these, redo the problems if you need help, and I'm here to help you. And then there is that open-ended question that I want you guys to tackle as well. Good luck.